We're going to look at simplifying radical expressions. Yep, those guys have not gone away yet. We know how to do it when it's single square roots and single cube roots, and that's essentially where we're going to continue. But we're going to look at, in particular, multiplication and division. So we're going to look at radicals that involve two or more radicals being multiplied and how you get the answer and then simplify it, and two radicals being divided and how you combine them and simplify the answer as well. I think it's pretty similar to what you've done. So let's look at some multiplication situations. Start off with a nice easy one. Suppose you had to do that calculation, the square root of 2 times the square root of 50. Now, we do not want the answer as a decimal. So essentially, you don't want to go near your calculator, even though sometimes, if you're lucky, it does give the same answer. We want to be able to do this in a better way. So the first step in simplifying this multiplication is to realize that you can actually take them inside and do a multiplication. So instead of the square root of 2 times the square root of 50, you can do a single square root of 2 times 50. And you might think, well, I wonder why that might be helpful. Well, it very often is. Do you recognize the nice number 100? Do you recognize that guy? Because it's got a nice square root, doesn't it? Come on, tell me what it is. It's not a secret.
10.
10.
Yes. You're thinking I was trying to catch you there. Right, it's 10. Let's try something a little bit trickier than that. How about the square root of 2 times the square root of 24? Now, when you put those two guys together, you're going to have 2 times 24. That's going to be the square root of 48. I guess I'll put it over here. These are the perfect square numbers, right? If you want to simplify a number like the square root of 48, and it's not like 100 where there's a perfect answer like that one, the square root of 100 is 10, then you have to, after spending all that time in putting these together, we're now going to take that 48 and we're going to split it apart. But I'm not going to split it apart as 2 times 24, because then I just end up where I started. The trick here is to find a big number from this list times somebody else. So 48 can be written as one of these guys times another number. And so the job is to find out what's the biggest number you can figure out that works with 48.
16 and 3.
Now, let's suppose times table is not your strong point. And this is a way you can tackle it, right? You know it has to be one of these numbers. So you type in 48. And, well, we can start at small one if you like. I like to start big and work backwards, but it works. Can you divide it by 4? Yeah, so that's a possibility. 48, can you divide it by 9? Nope, horrible decimal. 48, can you divide it by 25? Nope, horrible decimal. 48, I forgot to do 16. See how it works with 16? Not only do you get 16, you get the other guy. So if you've got a number, 120, 87, whatever that number is, you can basically write it in and divide it by each of these guys. And one of them hopefully is going to work. And if 2 of them work, pick the biggest one of the 2. So if tables are not your thing, maybe that'll be a little bit easier for you. it has to be a perfect match, right? So decimals like that mean you can't use it. So it has to be something like this guy like that. Now this fella, we know how he splits. Square root of 4 times square root of 3. And there's your answer. Are we good so far? Now you can extend this to 3 numbers. Probably that's the maximum that anybody would ever do it, yeah? So how about the square root of 3 times the square root of 6 times the square root of 12? And I'm going to show you an alternate method. This is 3 times 6 times 12, right? So 3 times 6 times 12. And you get the horrendous number 216. Okay. 216. Now, I don't think I'm going to do, I'm just going to go through this the same way, but I think I'm going to do it with a calculator. So I'm going to go 216 and I'm going to start at 81. So if you divide it by 81, it doesn't work. If you take 216 and you divide it by 64, doesn't work. You do 216 and you divide it by 49, it doesn't work. If you do 216 and you divide it by 36, hey, I got an answer. So it was 36 times 6. So do you see how I let the calculator do the heavy lifting for me? Yeah, I just needed to check against this list. And I found one that worked. And I know that's the biggest because I worked that way, right? Big to small. So the first one you get is the answer. If you go the other way, you might get an answer, but then later on a better answer. That's why I tend to go big and work my way down. So this guy is going to be square root of 36, which is 6, square root of 6. Now I said there is an alternate method. I'm going to show you this method once. And if you like this alternate method, then I can use it for the rest of the today or tonight. And if you prefer to just leave it alone with this method, we can do that too. So this is the alternate method. You go square root of 3. You write the square root of 6 as the square root of 3 times the square root of 2. And you write the square root of 12 as the square root of 4 times the square root of 3. And then you kind of mix and match. Those two get you 3. That guy gets you 2. And this fella, the little leftovers, get you the 6. So there is 6 square root of 6. Me personally, I don't like that technique, but I'm not saying you can't do it. It's just a different approach. So do you want me, when it's numbers, to stick to this technique, or do you want me to do this technique?
I like the original.
And I haven't influenced you by saying I like the original as well. Okay, that'll work. That does not mean that you can't say, God, that's much easier in my brain. I'm going to do them that way now. And you can do them either way to work. So I don't mind which one you choose. But let's move square roots and stick some variables in it. So we're going to simplify that multiplication. The technique I'm going to use is very similar to the number technique we just did, which is another reason I like that method. So you don't change methods. And you multiply these together. So 3 and 6 gets me 18. X and X gets me X squared and Y cubed. Do you recognize that this question is pretty much the usual simplification guy that we've done. Oh, it feels like a week ago. We did a week ago. Because to simplify it, you split it on out into the square root of 18, the square root of x squared, and the square root of y cubed. And each one of them gets simplified on its own, and then we stick the answer together. So basically, all you need to remember is to multiply these two guys inside the square root, and then break them apart and see what we get. Okay, 18. Do that one. How do you split 18? It's one of these numbers you use. 18.
9 and 2.
Okay. And 9 and 2. Can I just jump to 3 square root of 2? I don't feel I want to write everything down every time. Okay, that's that done. Color scheme. What is the square root of x squared? And don't make your life hard. What's the square root of x squared?
X.
Just x. What's the square root of y cubed? That's the tricky one, isn't it?
Is it y square root y?
Good start. It is y square y, right? And then that becomes what you just said, y square root of y. Exactly, it is. Now, you see I've taken each piece and found out what they are. And to finish with, 3xy, and then these two go inside their own square root. Do another one. We need a few of these before I feel comfortable. How about 2y squared z times 8y cubed z squared? Now, I'm going to try anyway to save some lines by doing things in my head. If you multiply these two together, you can put them inside the square root. So the 2 times the 8 is 16. The y squared times the y cubed gets me y to the 5. And a z times a z squared gets me z cubed. Are you happy with that, or do I need to write this down and then that? Are you okay with these two becoming that?
I'm good with that.
Good, because it's good for notes that you put everything in, but once you get comfortable, it's okay to miss some lines out, right? Just do something in your head and not always write it physically down, except in exams where I write everything down. Right, this guy is going to split as a square root of 16, a y to the 5, and a z cubed. And I won't do a colour scheme. Square root of 16 is actually a perfect answer. It's 4. That's nice. The y to the 5. Okay. If you simplify the square root of y to the 5, you actually get 2 bits. Don't you get a power of y and then a bit left over, a square root of y left over? You can think of halving the power. If you halve y to the 5, don't you get 2 and a bit left over, right? So 2 means y squared and a bit left over. So maybe that's the way to look at these square roots. Think of dividing by 2 and then see what we get. Okay, if you take cubed, right, this third power, and you divide it by 2, you get 1 and a bit left over. You get 1z and a bit left over. Maybe that would be a helpful way to look at that. Now you put the package together and you get 4y squared z, and these two inside the square root. Multiplying's not that different, isn't it? It's, from, simplifying these guys, right? I mean, it's really, once you've multiplied them, isn't from that point onwards the same kind of simplification questions that we've done before. Right, let's try one last one of these and then I'll give you something to try. Let's go crazy. 3ab times 2ab squared times 15, that's a good choice, ac cubed. Okay, if you multiply them together, let's do the numbers. 3 times 2 is 6. 6 times 15 gets you 90. There's an a times another a times another a, so that gets me a cubed. There's a b times a b squared, that gets me, oh, I didn't realize I was going to end up with this, and a c cubed. So that's going to split as a square root of 90 times the square root of a cubed times the square root of b cubed times the square root of c cubed. Okay. In a lot of ways, the numbers can be harder to do than the powers. Right, I need somebody in this list that should play well with 90. Yeah, I found somebody. It's not that exciting. But can you find the two-number deal for 90?
9 and 10.
Yeah. I thought there'd be some bigger, but there wasn't. So it's 9 times 10. So that's going to get me 3 square root of 10. Great. That's unfortunate. These ended up being the same. But in a way, it's easy. Because once they know what the answer is, it's pretty much going to look the same for these two. And what's the square root of a cubed going to get you?
A squared times a.
Right. And then when you split it, square root of a squared gets you a square root of a. And then won't this be a b squared times b, which gets you b square root of b. And this is going to be c squared times c, and that's going to get you c square root of c. And a lot of people might not do this line at all. They might just jump, from one to the other, and that's fine. Tidying up now, that's all I'm doing. Is 3a, b, c, and a big square root made up of 10 a, b, c. And that's essentially the process for multiplying and simplifying radicals, right? So let's give you something to try. I think I'll give you 3. There's one with numbers. There's that guy. And then a ridiculous one. Okay, you got 2 minutes. See how many you can do. Okay, let's go. See how many you got. Multiplying these two together gives me, I believe, 150. So I guess the challenge is, did you find a combination that works with 150?
Got 25 and 3.
I've got 25, which is correct. But how many 25s? Check again, it's not 3.
6.
Yeah,
That's what it
sure she
said.
would have got. Yeah, 6. You might have saw 6, but you didn't do it. Now, if I'd planned ahead, I would have actually done more room, but I'll squeeze it here. The answer is 5 root 6. So you're done. You did the hard part, getting to 25. Right, in this case here, the numbers give you 81. You have an a cubed and a b to the 5. So it's going to split as a square of 81, a square of a cubed, and a square root of b to the 5. Well, that's definitely 9. So that was an easy one. How's the square root of a cubed going to come out? Kind of done this before, didn't we? A cubed. Square root of a cubed. What do you get? That guy? It's okay to be wrong. I'm wrong lots of times. Ask my wife. No takers? A square of 8. Now, if you do b cubed, sorry, b to the 5, divide it by 2. Right, 5 divided by 2 goes twice and a bit left over. The twice tells me it's b squared, and the bit left over tells me it's the square root of b. That's how I figure that out. Now, you put that package together, because again, I never gave myself enough room. You're going to have a 9, an a, and a b squared, and then you're going to have a square root of ab. Right. This fella here. 2 times 3 times 6 gets me 36. And a times an a times another a gets me a cubed. A b times a b squared times another b gives me b to the 4. And a c times a c squared times a d, c cubed, gets me c to the 6. So hopefully if you got to that question, that's the big ugly square root. It's going to split now into 4 pieces. It's going to look like that. Square root of 36 is actually a nice one. Isn't that a perfect square? So we get a number out of that. So we got 6. I'm going to keep asking this question. Eventually, I'm going to bore you to the point where you're just going to answer it to stop me asking. What does the square root of a cubed get us?
A over squared A.
There we go. Now, what about the square root of b to the 4? That's a bit different. If you half 4, oh, it works out perfectly, right? There's nothing left over.
Just B A B
What power? Half of 4.
Squared.
Squared.
Yeah. And this guy, well, if you half him, doesn't it work exactly? Nothing left over. So what power will you get when
B
you half?
to the
There we
third.
go. To the third. And then make it look pretty. And there we go. So if you want to multiply and then simplify radical expressions, there's your technique. Any questions, or are we good? Last chance? Okay. Quiet is good. Now going to look at division. And there are basically going to be two situations. And the two situations are going to be, you're going to do divisions of numbers and expressions. And the regular kind come out nice. And there is maybe fractions, because it's okay to have fractions in the answer, but there won't be any square roots on the bottom. So a regular question is one that when you've got the answer, there is no square roots in the bottom. And then the second kind of situation that's going to happen, we have a technique that's called rationalize the denominator. And you have a division and you do the same process, but when you're finished, typically it's a fraction, there is a square root on the bottom, right? So you have an answer like 5x, and on the bottom, the square root of y, right? Or the square root of 3, or the square root of anything you like, right? And when that happens, we're going to show you how we fix it. Now let's do some regular divisions before we worry about what that special case looks like. You're the first person in the world to see that. Pretend you are. And you want to find the square root of 12 over 2. Right? And don't overthink this. What do you think the answer should be? No, it's not a trick question.
6.
Yeah.
I was gonna say, so, yeah.
Yeah. Sometimes the obvious answer is the right one. And then you look at 6 and you check it out and you say, yep, that's it. Can't do any better. Now, you might get divisions that look like this. Now, they're very similar, but do you notice that this one has a single square root and this has two separate square roots? That's pretty much the only difference. And we're dealing with numbers right now first. Now, what you can do is very similar to the multiplication. Don't you bring them inside a single square root? And then you divide them. So those two square roots, one divided by the other, turns into this guy. Now, it might be that that's the answer. You know, like the square root of 6 is the answer. But it might not be, because sometimes don't you have numbers that you can simplify? So scan over here. It's one of the, I mean, if you do enough of these, you actually end up seeing pretty much all the numbers that could happen, right? So square root of 20, I'm sure we saw that guy before. How would we split the square root of 20? I want to simplify it. Who do I use for 20?
4 and 5.
4 and 5, yeah. 4 and 5, which splits as the square root of 4 times the square root of 5. And that gets us to square root of 5. And some of you might not need that line. And you go from here to the answer. And you're finished. So technically, aren't we dividing two square roots, two radicals? This ugly thing is actually the same as 2 square root of 5. Now, I kept deliberately away from calculators, but I want to show you one thing that you can do with a calculator is suppose you had an ugly combination of numbers and you have a nice answer, but you know, your times table's a bit shaky and you want to just be sure that you did it correctly. You can go and you can do the square root of 40, like that, divide it by the square root of 2, and you'll get an ugly decimal. Then take your answer, 2 times the square root of 5, And you should get the same ugly decimal. What that is telling me is that this guy is worth the same as that. It means I did not screw up, right? I know I've got a good answer. You know, because sometimes you do it and you say 4 when you meant to say 8, you know, you did something else somewhere else. You know, you lose a digit or whatever. And that's a kind of numerical check. You don't really need to do that in WebAssign because it tells you when you're right and it tells you when you're wrong. But it's a quick way of doing it. Right there for a little while. How about square root of 14 over the square root (28). Now, when I combine these two guys, we get that. And that actually simplifies down to a half, right? So you should always simplify your fractions. And now we've reached the second situation. This thing splits as the square root of 1 over the square root of 2, and that gets you 1 square root of 2. So do you see that I have an answer, but it has a square root in the bottom? The technique I'm about to show you is how you remove that square root. How do you rewrite that guy so there isn't any square roots in the bottom? We call that, rather mouthful, rationalizing the denominator. And I'm just going to write it again because I need some room. The way you fix any square root that's on a fraction and it's in the bottom, right? I don't care if it's in the top. On the top's fine, but I don't like it to be in the bottom. The way you fix it is you multiply by a special version of 1. And the special version of 1 is whatever that guy is. So you see how that guy's the square root of 2? This is a special version of 1. Now let's see what happens. If you multiply the top together, you get square root of 2. If you multiply the bottom together, you get square root of 4. Well, wait a minute. There. Now you might say, I like that answer. It's nice. I don't see why I bother having to do the extra work to get that answer. But in mathematics, we have rules about how things should be written. And we have a rule that says fractions can't have square roots in them. Not, I'll rephrase that. Fractions can't have a square root on the denominator, right, on the bottom. And everybody has agreed on that. So all mathematicians, when they do work and they do quite extensive work, always refer back to rewriting their answer like that. Now, some of you are eventually going to go on and do pre-calc 1 and pre-calc 2, which is algebra and trig. And trust me, especially in trig, you're going to have to deal with this problem, that these things have to be written like that. So it will come up again for some of you. Now let's look at another fraction. How about square root of 3 over square root of 12? That's going to be the square root of 3 on the top, 12 on the bottom. That's going to be the square root of a quarter. And that's going to split into these two square roots. Square root of 1 is perfect. Square root of 4 is a perfect square. Do you see in this case, we don't have a problem. As long as there's not a square root in the bottom, we don't have a problem, right? The answer is fine. In fact, a half is fine, no matter what you think about it, right? It's a great answer. So here's a kind of third possibility that could happen. Try and make this work. It's hard to actually make questions work when you're not working. There we go. Now that ends up being, oh, shooting spice. I meant 32. Okay, there, I fixed it. Square root of 10 over square root of 32 gets you 10 on top, 32 on the bottom. That simplifies. What does the fraction 10 over 32 simplify down to? What can you divide top and bottom by to simplify it?
Two.
Yeah, it's the only thing I could think of as well. Right, so you always simplify. Then you split it up again. And this time, there's a square root of 5 on the top and a 4 on the bottom. But that's the answer. It's okay to have a square root on the top, because sometimes you can't avoid it, right? You're going to get a square root somewhere. But the rule is, on the top, fine. On the bottom, nah, you got to do this rationalize the denominator thing. So far so good. You only need to fix it if there's a square root in the bottom. It's okay to have a square root on the top as long as the bottom doesn't have one. Let's do some more rationalizing the denominators. Let's suppose I did a question and it ended up coming out like that, right? So I won't make up the question, but we did it, we cancelled it, we broke it apart, and we're now at this stage. Square root in the bottom, bad news. Special version of 1 we're going to use. Whatever that is, that's the special version of 1 that you use. So the top becomes 4 square root of 3, and the bottom comes 3, and we're finished. Suppose I got 6 over the square root of 3. Right, suppose that happened. Then I'd still multiply top and bottom by square root of 3, and I'd get 6 square root of 3 on the top, and I'd get 3 on the bottom. And you might think, right, great, finished. Look again. Can you do anything to simplify this answer here? Anything you can cancel to make this
And
nice?
divide by
The
3.
3 cancels
Yeah.
out.
And they cancel out. And actually, the answer looks like that. So if you think about it, that was the original question, and this is the simplified answer. I don't know about you, but that looks nicer to me. Can you see that sometimes rationalizing the denominator can actually help make the thing look nicer? Right. We just don't like square roots in the bottom. They are horrendously ugly things to deal with in math, so we kind of try and avoid them when we can. Okay, so I'm going to give you some questions to try out. I think I'll do 3 again. And at least one of these is going to have a rationalize the denominator problem, right? And it might be the first, second, and third hook. Yeah, it might be all 3. You'll find out. There's your first one. There's your second one. This is your last one. Okay, we take those. 2 minutes, go for it. Two of these end up being rationalized as denominator. Some of you need a kind of head start. That would be your first line. Come here. You are. You want up? Oh God, you're a weird one. Come here. Let's get you this way. Ups and daisy. Oh, there we go. Oops. Hi everybody, this is Bailey paying us a visit. He needed some attention. Oops, he's looking at you. You can see you on the screen. Okay, that was it. Whoa, whoa, be careful. Good boy. Okay, time up. This guy becomes 2/3. And then you break it apart, you got that guy. Would you agree this is one of the rationalized denominator guys? Right, square root on the bottom. So I'm going to do a √3 top and bottom. And on the bottom, these get you 3, and on the top, hopefully you got square root of 6 on the top and a 3 on the bottom. So give yourself a pat on the back if you did that. What fraction does 10/75 separate down to?
2/15.
That's going to separate as a square root of 2 over a square root of 15, right? Is this one going to be a rationalized denominator question? You agree? Rationalize the denominator. So you get this guy, and the top is the square root of 30 and the bottom is 15. And this one, well, what does this one get you? Well, it gets you the square root of 12. And the square root of 12 ends up being 4 times 3, ends up being 2 square root of 3. So that one didn't have anything really ugly to be done to it at all. So dividing radicals, right? Dividing square roots when they're numbers. So let's look at expressions, right? Let's just stick in powers of X, Y, Z, A, B, C. Now, in this question here, the number on the top's 19, the number on the bottom 16. So they have been cancelled down as far as that goes. So if that's the case, then what you do next is you split it into their separate pieces. The square root of 19 is just the square root of 19. There isn't any combination here that's going to change it, so leave it alone. Would you agree the square root of 14 is a perfect 4? And what about the square root of x squared? What would that get you?
Just X.
Just x. There, that question wasn't too bad. By the way, this is question 19 in the homework. Right, see if I can find some. Here's one, a little bit trickier. This one is similar to question 28. So we have 360 xy cubed. Don't like that so much. Let me rewrite that. I made a mistake. 360 xy cubed and a separate square root of 3xy in the bottom. Now we're really having problems. Two single square roots become one single square root. So you always kind of have this process of putting them together and then breaking them apart. So I'm putting them together now inside a single square root. And forget about the square root for a minute. It's still there, but it's not going to take part in what I'm about to do next. Let's go cancelling. Anything here cancel?
X's.
Okay, one for one go, they're gone. Anything else cancel?
Can't you divide by 3?
Yeah, and you get a 1 there and you get what, 120 there. Anything else go? Can the y cubed and the
What are
y
the-
at least?
The Y's go.
Yeah, one of the y's go, and that leaves you with y squared. It's a bit hard to see with all these crosses, but what is left is 120 and a y squared. You don't really need to say over 1 because, you know, that just means it's a whole number. So in this particular one, we got that. And now we split it. And the square root of y squared is an easy one. I need to figure out what to do with the square root of 120. Right? I'm pretty sure that can be simplified. Any ideas about what the combination would be for 120? And I think there's actually a couple, but try and pick the biggest one. R120 plays with one of these guys. Well, it's a bear. I'm going to double check now I've said that. Oh, I take it back. There's only one. There's not two. There's only one combination that works. Anybody found it?
Is it 4 and 30?
Yeah. I was thinking in the back of my head that there was a bigger number. That's why I originally said there's two. But the big number that I thought worked didn't. So I threw it out and said, okay, there's only one left. Let me double check it. And this guy becomes 2, right? This guy becomes square root of 30 with a y. And I'm happy with that. You might find in some textbooks, they write it like that. You agree it's the same guy. I think the reason why some textbooks do that is they have a kind of, you know, square roots go at the end kind of rule, right? They're the ugly guy. Stick him at the end, stick everything else at the front. But I don't care. Both of these are fine. So far, so good. Try another one. See if I can find one. They're kind of scattered all over the place. Not that many of them, but there are a few. I've done that one. Oh, let's try this one. 18. So the square root of 5 over 49 a squared. So in this case, there isn't really anything to do except separate. Right, they're already as a single fraction. There isn't anything I can cancel. So we've got this. Can't do anything with the square root of 5, so that's finished. What about the square root of 49? Can that become something? Square root of 49.
7.
Yeah, nailed it. And what's the square root of a squared?
Just A.
Just a. And there's no square roots in the bottom, so we are finished. So you don't really get too many fraction division ones to do, right? Most of the questions are multiplication ones, and that's fine. They're just less, they're less likely, I guess. I think we need a break for 5 minutes. So why don't you go and stretch your legs, have a coffee. I'll see you back here at 25 to. Well, hi everyone. I think my dog just told me it was time to get started. Can you hear him in the background? That's him. Yeah. You probably saw a leaf or something. Okay, we're on to a new topic today. This evening. We're actually on to the, if I can, where is it? There we go. Right, we're on to this idea that if you can multiply and divide radicals, right? Surely you should also be able to add and subtract them, right? Okay, WebAssign has just been a pain in the butt right now. Figure out what it's doing. Try that again. Okay, we're good. I should be able to, there we go. I can do it now. So you should be able to add and subtract. The good news is that it's relatively straightforward. There's not too many bits and quite a lot of overlap. In other words, you do stuff that you've all done before. So suppose you're going to add or subtract two or more radicals. The first step is simplify all the radicals, and then the second step might seem a bit cryptic, but you collect similar radicals together. So that's going to be the gist of it. So let's get you some warm-up stuff, things you need to be able to do to get that done. Do you know the square root of 7 plus the square root of 3 are totally different objects? Just like x plus y. And what's the usual thing you've probably heard people say, right? You can't add apples and oranges, right? You know, that kind of thing. Okay. So, what's the answer to that? The answer is a kind of boring. That is as good as that's ever going to get. You cannot add two different square roots together. So even if you wanted to, because you want it to be true, it's not true that the answer is the square root of 10. So the first thing we're going to learn is what you can and what you can't add. You cannot add two different guys. It's a bit like me saying you can't add x, add y, right? That's as good as it's going to get. On the other hand, you can do this. As long as the square roots are the same, exactly the same, you can add and subtract them in the usual way. Think of it as I've got 3 somethings, I add 2 somethings, that means I've got 5 of them. 5 somethings take away 6 somethings means I have got -1 something. Does that make sense? That if it's the same square root, you can add and subtract them? Suppose you had 2 square root of 3 and you wanted to add 5 square roots of 3, the answer would be 7 square roots of 3, right? That is the basic building block. As long as they are the same square root, the same radical, you can add and subtract them. So you might get things like this. It's very similar to what you would do in algebra. Remember in algebra, you had a thing where you said collect like terms. Remember that phrase, collect like terms. So in this world, those two guys belong together. So I collect them together and now I add them. And then these two guys, they belong together. And this is the answer. If you take those 4 things, they become these 2. And you stop. Would you agree these are 2 different radicals? You can't add, subtract 2 different radicals. You can multiply and divide them. We've done that, but you can't add and subtract them. Here's a strange one. I'll let you look at that one for a few seconds. This one is sneaky. And it's not that you don't do the same process. You do the exact same process as we did here. And the sneaky part is in what the answer eventually looks like. Okay, so if I collect these two together, I get 4 root 7, take away 3 root 7. And if I take these two guys together, I've got 2 square root of 3, take 2 square root of 3. I normally call this process shuffling the cards, right? We're just rearranging the order that the cards are in. We're not changing anything else except the order. Now, what's the sneaky part? And maybe it's not a sneaky part. Maybe to you it's obvious. What does 4 square root of 7 take away 3 square root of 7 get you?
1 square root 7?
Do you think we write the number 1, or do we think you
Would
only
need
just
it.
don't need it? That's what's sneaky about it. Do you know in algebra we keep saying to you, don't write 1x, you don't need the 1, just write x. Exactly the same kind of argument. Don't write 1 square root of 7, just write square root of 7, right? You don't need the 1, right? Square root of 7 is good enough. Now, what about this next one then? What does 2 square root of 3 take away 2 square root of 3 get you?
Just square root 3?
Nope. Not this time. That was what happened here.
0.
But yeah. Now, do you think you write plus 0? No. You just leave it alone. In other words, that's the answer. Do you know if you were doing math, if somebody went and said to you, 4x take away 3x plus 2y take away 2y, wouldn't you call that x and wouldn't you say they disappear and the answer would be x? It's essentially the same, isn't it? You don't say 0 square root of 3's. There's no need to. You don't even say plus 0. There's no need to, right? Plus 0 doesn't bring anything. It doesn't help. It's not necessary. Are we good? Right, so now we're going to go back to these two steps and look at adding and subtracting. So I'm going to start with a question that looks like question 1 in the homework. It's a square root of 2 plus the square root of 8. Now step 1 says simplify all radicals. I don't think I'm going to get any simpler than the square root of 2. Would you agree that you can simplify the square root of 8? And you might do that over here as kind of side working. How would you split the square root of 8 to simplify it?
Square root 4 times square root 2.
Okay. And the square root of 4 gets you 2 times, so 2 root 2. So this guy is 2 square root of 2's. So that's basically my step 1, right? Simplify all the radicals. Now we're getting there. Step 2, collect similar radicals. Would you agree these two guys are the same, right? They're both square root of 2's. And as long as they're both the same, exactly the same, I can add them. So how many square root of 2's do you have?
2.
How many? You might be right, I just didn't catch it.
2.
Do we? We've got, how many is that? 1. How many is that? Another 2. So what do we have?
3.
Agree, Rachel? 1 plus 2 more? 3?
Okay, yeah, I see. Okay.
Got it? Finished. That's the answer. Let's scroll down, look at the next guy. Oh, God,
So it's 3 because you added the.
yeah, it's a bit like,
It's like an
There's not-
invisible one, kind of.
yeah,
like
they're
the
an
minus
invisible 1 here. Yeah, that's a good way of
Okay.
saying it. They're an invisible 1 plus 2 more is getting you 3, right? Although you don't write it, I mean, I guess you could write it if it helps you get the right answer. Right, I just took a look at question 2 and I'm kind of regretting the fact that I chose question 2. I've committed, so I'm going for it. And the reason that I don't like it is that guy. Okay, so over here is the square root of 27, and I'm going to do this working on the side, and once I've simplified it, I'm going to write it here, and then after that I'm going to do the square root of 192, and once I've simplified it, I'm going to write it here, and hopefully these two guys will play well together. We are going to be so good at perfect squares because of how many times we needed to use them. What is 27 going to become? I need a combination, and one of them has to be a perfect square, one of these numbers. Who's 27 going to be?
9 and 3.
Okay. And can I jump to 3 square root of 3 now without doing all the intermediary stages? Okay. So I know this guy here is 3 square root of 3, so that's a good start. The one I was dreading, 192. I do not know what that guy is, but I am going to take a guess. Normally, don't we go for the square number and then see what's left? But in the context of this question, does it seem reasonable that one of the numbers is going to be 3? So I'm going to check that out and see if my premonition, or whatever you call it, was right. If you take 192, does it divide with 3? And it does. And doesn't it give you a nice number? So I kind of found the good number backwards, but I still found it. And that guy,
Can you do 16 and 12?
you could, but 12 then could become 4 times 3, and so eventually you get the same answer. So first I'll put this one in, and then I'll try and explain what I just said. So quite sensibly, she said, couldn't we do, I forgot what you said. What was the combination again?
16 and 12.
Right, 16 and 12. And that becomes 4 times the square root of 12, which is good. Nothing wrong with that. Oh, wait a minute. Can't 12 be called 4 times 3? And that becomes 4 times 2 square root of 3. And guess what? You still end up at the answer. It's a little, the analogy here is it's a little bit simplifying fractions. You know, sometimes you simplify a fraction and you divide the top and bottom by 5. And then you find out the answer's 4/8 and you say, oh, wait a minute, I could do better and get a half. Right? Yeah, as long as you go until you can't go any further, and that to me is you can't go any further, you're going to get the right answer. Now, in this case here, these two guys are the same, so I can add them together, and now I have 11 of them. Any questions so far? We're doing okay. We feel good? Okay, let's just keep fighting our way through these guys. It's kind of well, it had to happen sometime, so I might as well do it now. This one is the square root of 81y z squared plus the square root of 9y z squared. And we are going to add these two guys together. And I'm going to do my little working on the side thing. But it's going to get a little bit messy because the guys we're working with are just kind of big. So it's going to be the square root of 81, the square root of y, and the square root of z squared. And the square root of 81 is a perfect 9. Can't do anything with the square root of y. Can we do something with the square root of z squared? What's the square root of z squared? Oh, by the way, this is question, I think it's called question 5. This is not a trick question. What's the square root of z squared equal to?
Z.
Yeah. Did you say z there? Alyssa, you didn't say Z. Rachel,
Yes.
it's not Z. What letter of the alphabet is it?
Z.
C. Alyssa, shame on you. You should be embarrassed. Are you suitably embarrassed now? Z in it. Can't take you anywhere. There we are. 9 square root of YZ. Let's do the other one. 9YZ squared. That's going to split as the square root of 9. The square root of Y. Oh God, it's almost the same question. Okay, let's give you a chance to redeem yourself. Alyssa, what is the square root of Z squared?
Z.
Well done. Yeah, that wasn't so painful. Right. So this guy was 9, and I'm going to rearrange the order. 9Z square root of Y, because it looks prettier. And this fella here is 3Z square root of Y. Now, when you look at these two guys, would you agree that they're the same, right? Similar terms. So 9 of these guys plus 3 of these guys means I now have 12 of these guys. Do you know when you move on to your next math class and you get whoever you get, you know you're going to say 5Z or something when they ask you an answer, and you can say, oh yeah, the answer's 5Z. And do you know what the professor's going to say? You got Professor Robertson, didn't you? I've had students who've came back and visited the college, and they've went to university, and when they got to university, one of the guys had kept on saying Z a lot, and his professor went and said, did you have a British professor? Because we say Z a lot. So don't feel bad about it, Alyssa. If you want to say Z, you are allowed to. But if you do, I will make fun of you. So I'm telling you that right now. So it's your decision how you want to play that one. Are we comfortable with these questions? Are we good right now? Okay. So I'm going to show you a version of, I think it's called question 9. And I'm not going to say anything except what's the answer. I see your lips moving, and it looks like they're moving with the right number. How many do you get, Rachel?
10
You do.
square root 5x.
I want to call it a trick question, but isn't that a very easy question? Couldn't you make your life really difficult by trying to do all sorts of clever stuff of breaking things apart and seeing what they could turn into? And in this question, it wasn't necessary. However, in this question, all bets are off. When you look at this question and compare it to that one, can you see why this question needs more work and why that one didn't? Does that make sense to you what I'm saying? This question needed more work, that one didn't. Now, when I look at them, do you see that they're not exactly the same square root, right? They have different values, 16 and 25, for instance, right? So a lot of it's the same. The y squares and z's are the same, but not the numbers. So when I see something like that, I know that I'm going to have to break it apart and do all the other stuff. So let's find out what this guy simplifies to. And you have the square root of 25, the square root of y squared, and the square root of z. And the square root of that guy is 5. This fella is y square root of z. So, pretty nice. Take away 16 y squared z. That splits as a square root of 16, a square root of y squared, and a square root of z. And that guy's 4, that guy's y, and that's still a square root of z. And 5 of these, take away 4 of these. Oh, could get caught out here. What is the answer to this question, which by the way is question 10?
Y square root z.
Did you say squared there, Jamie? Did you mean to?
Not square like the square root.
Right, like y square root of z. I got you.
Yeah.
5 is some, take away 4 is something, you're left with 1 is something. And we don't write the 1 because it's not necessary, right? We don't need it, so we don't write it.
That was question 10.
Looks like question 10, yes, on my list. My list might end up being slightly different from yours because the numbers change as well, as you know by now. WebAssembly keeps randomizing things. Square root of 18, take away square root of 50, take away the square root of 98. No help, go for it. What do you give you? Give you 2 minutes. I think if you do it correctly, there's a square root of 2 in the answer. Okay, you up for it, Savannah? I'm going to give you the first part. Give me 2 numbers that give you 18. One of them has to come from here. So give me the split on 18.
9 and 2.
Great. So that gets you 3 square root of 2, so that goes there. Right, I'll take a volunteer. Give me the split for 50 now. How's 50 going to split?
25 and 2.
I think I heard it. And that's going to get me what? 5 square root of 2s. So take away 5 square root of 2s. Oh, 98.
49 and 2.
49 and 2.
Yeah. Did you notice that it's kind of obvious there's probably going to be a 2 in it? So it wasn't as bad as it might have looked. And that's going to get me 7 square root of 2s. And what do I get? Well, I get a negative number, which is a little bit different. I believe you get negative 9 square root of 2s. We gotten well with these guys? Adding and subtracting? Thumbs up. I like thumbs up. How about this one? 14. 6 cube root of 7y plus 3 cube root of 7y. Just to show you can do it with cube roots. Don't overthink this one. What's the answer?
Nine.
9 cube root
Cubed root.
7y.
7y.
Yeah. No, it's okay. I don't mind you both saying the same answer. It's a good sign. Can you see that question was almost not a question? You didn't have to do anything. You just had to realize that they're the same thing. So always go for that as your first kind of look. Hey, if they're both the same, just add them. Don't even worry about breaking them apart just to put them together again, because it's probably not going to do anything. If they're both the same, just add them or subtract, I guess. Suppose this happened. What would the answer be if that had happened in WebAssign? What would you write down in the box?
0.
Yeah. 0. Okay. Well, that's pretty much all I want to do with the add and subtract world. There is an application that we're now going to use. And we're going to use a thing called Pythagoras' theorem. I don't know, have any of you ever heard of it? It's hard to tell what you've done way back in the day. Right. We're going to use Pythagoras' theorem. We're going to do essentially find missing sides on right angled triangles, which is what Pythagoras' theorem was designed to solve. I want to tell you an allegedly true story. And the reason I'm saying it's allegedly true is because I read it on the internet. And I've read all sorts of stupid stuff on the internet, which I know is not true. I've read that there's 2 White Houses. There's the one that President Biden lives in, and then there's this other pretend one that they use for some reason from time to time. Total lie. I read it on the internet. My nephew, for instance, just to share a little story with you, saw a video that said you could, if you were stuck in the forest and you had no fire, you could actually use an orange peel to start a fire. And they showed the video, it's probably still out there, where they took the skin of the orange and you turned it upside down and you got a little stick, like, you know, you rub the stick thing, and you rub the stick like dead fast. And evidently there's, you know how there's liquid in peel when you squirt it, it gets in your eyes? Evidently that was meant to be really flammable, and it was easier than doing the 2 sticks thing. And it is a total lie. He was convinced about it. So What you then have to do is you have to do another internet search where you do orange peel sets fire hoax. Stick the word hoax at the end, and you will find someone who's figured out that it's a big hoax. So the story I'm about to tell you, I believe it's true, but it could be a hoax, right? Pythagoras was a Greek mathematician way back, thousands of years ago. And he discovered a property in right-angled triangles. This part is not argued. Everyone kind of agrees on this. And he found out that if you take any right-angled triangle you like, and the two straight ones, right, the ones that make the corner, we'll call them A and B, and the third one, which is called the hypotenuse, we'll call it C, he discovered a very simple connection. And it was the length of this side squared is the same number as the other two guys squared and added. And that's called Pythagoras' theorem. And what that allows us to do, it allows us to find the length of one side of any right-angled triangle, provided you know the other two. Right, so you can tell me any two of the three you like, and I'll get the third one using Pythagoras. Now the hoax or true story. It was a secret. It was such a useful thing. You may not think it is, but it's actually very useful. It allows you to do right angles very easily. It allows you to do construction. It allows you to get the answer to questions that other people couldn't. And so he kept it as a secret, and he only shared it with a group of mathematicians who happened to be called the Pythagoreans. And it was like a secret society, you know, the kind of societies where you have a little secret handshake, that kind of society. And in this society, the mathematicians would share each other's kind of secrets, and Pythagoras' was like the ultimate secret. But other people said, hey, have you seen this clever thing that I've figured out, or that clever thing? But they kept it within themselves. You know, like knowledge is power. You know, don't share it, because if everybody knows it, then it's not worth anything. And it was kept secret for quite a long time. And according to the story, there was one woman mathematician who was in the Pythagorean Society. She was one of the members, and she found out, because she was a member, she knew his secret. And she went and talked. She told her lover, who wasn't in the society, that he was a blabbermouth, and the secret got out. And allegedly, that's how the secret got out. Whether that story is true or not, but there's an end to this story. The Pythagoreans were not too happy when they found out that one of their biggest secrets had escaped and everybody now knew about it. Right? Power is important to them. So they found her and they caught her, and they took her out to the Aegean Sea, and they wrapped her up with a big rope and a big heavy weight, and they chucked her over the side and killed her. So she died, allegedly. So go look that story up and find out if it's a hoax or not. The secret of Pythagoras. So back to this nice guy. Suppose I give you a right angle triangle, and I tell you that this side is 5 and that side is 7. And I want you to find this side here, and I'll call this side A. So let's just call the sides A, B, and C, right? The two horizontal and vertical ones, we'll call them A and B. And the long sloping one, the one they call the hypotenuse, we'll call that C. Now, according to Pythagoras then, C squared, which is that guy, is equal to A squared, which is that guy, plus B squared, which is that guy. So I now have 7 squared, A squared, plus 5 squared, right? So you plug in the numbers for the two that you know. In this case, I know that one of them is 7, the other's 5. 7 squared is 49. And 5 squared is 25. And now we're going to solve an equation. Okay, solving equations. As long as you do the same to both sides, it's okay, roll. Tell me what I should do to both sides to get closer to the answer.
Subtract 25 from both sides.
Right, now if you take 25 away from that, you're going to get 24. Now, in a really nice question, wouldn't that number there be a nice number like 36 or 49 or 64? Because then we could take the square root of both sides. And I am still going to do that. And the answer would be a positive number because it's a side, the square root of 24. But there's a little kicker in the tail here. You think we are going to put that answer into WebAssembly? What do you think we could do to make the square root of 24 nicer looking, at least for the mathematicians?
Simplify it.
Okay. What's the split for 24? How do you split 24?
Four times 6.
Yeah, there's not a lot of choices. 4 times 6. Can I save a line and say 2 root 6? Are we good? Yep, do another one. Yeah, I'll put it here. This time we're after the hypotenuse, right? The C guy. Well, C squared is A squared plus B squared. C squared is 8 squared plus 4 squared. 64 plus 16 gets you 80. And that means C is the square root of 80. I need to split 80. What's the split for 80? Nobody got one? I got one. One of these guys works with 80. Who is it?
16 and 5.
There you go. And that's going to get you the answer. So that's basically a Pythagorean, Pythagoras' theorem being used to find missing sides. The only difference is that we're choosing questions where the sides aren't nice numbers. They are radicals that we can simplify. And then they, in the homework, have added an extra twist. Let's see which one this is. This is question 6. It's my question 6. And the triangle is still going to be called A, B, and C. And in this triangle, they tell you A is 3/10. And the extra little thing that changes the story a little bit is that this angle and this one are the same size. And our job will be to find out what B is and write the answer kind of in here, and then to find out what C is, and you're going to write it in here. Now look at this question carefully. they've only really told me that side, right? But I know what B is. And I don't need Pythagoras to figure it out. Because even if my picture doesn't look right, if this angle is the same size as that angle, does it make sense that this side should be just as long as that side? Right? So if this is 3/10, so will this be. So if you get a right angle triangle and the two angles are both 45, which they'll have to be, then A and B will be the same number. Now that means I now know this guy is 3/10. So now we're going to do Pythagoras' theorem to find the third missing side. Because you can't do Pythagoras until you know two of the sides. So we keep him to the last question. So A is 3/10 and you square it. And B is 3/10 and you square it. If I showed you how to do fractions on the TI-84, I think I have, but I might have forgotten. Okay. This is kind of cool. If you go 3 divided by 10, you get that guy, right? That's decimals. You might think that's not going to work. Watch this though. Brackets. 3 divided by 10, close the brackets, squared. So that's this guy. Plus, put another bracket in. 3 divided by 10, close the brackets, squared. So that's that guy. Now I'm going to hit enter and a decimal is going to appear. But we don't want decimals. None of the questions we've done have decimals in it. So what you then do is, once you've got the answer, hit the math button. Choice number 1 is fractions. And then hit enter. And just like magic, the answer. You want to see that again? Just randomly doing fractions. Suppose I had 3/4 and I wanted to square it, and I want to add it to 5/6, and I wanted to square it. So you just type in that guy squared plus that guy squared. There we go. Hit enter, and then just do math button, choice 1, and hit enter, and the answer would be 181 over 144. Now, does that make fractions so much easier if you let the TI-84 do it? And it works for anything. It doesn't need to be squared. Suppose it was 4/5 take away 6/7. Right? There's the decimal. Then just hit math, and it will turn it into a fraction for you. So 4/5 take away 6/7 is negative 2/35. And now you've got fractions. That's cool. Oh, back to our question. There's c squared. Now to get c, you find the square root. We want to simplify this guy, don't we? We want this guy to be as simple as possible. So I can't cancel it, it's done. I can split it. And I like the top number. Is there anything you can do about the square root of 50? Can we split it and simplify it? What can you do with 50 then? How does it split?
25 times 2.
Right. Which means that we're going to have 3/5 square root of 2's. And I'm going to write this guy over here. Oh dear. Do we like square roots to be in the bottom of a fraction? No, we don't. That's called rationalizing the denominator, right? We are going to fix it. What special version of 1 is going to fix this guy?
Multiply it by the square root of 2.
Yep. And the top then becomes 3 square root of 2's. And what do these two guys get you? Well, they get you 2, but it's 5 lots of them. So 5 times 2 is 10. Are you happy about the 5 and then the 2 become 10? right? 5 times 2 becomes 10. And there's the answer. So do you see how knowing how to rationalize the denominator can pop up in some of the most, oh, I didn't think it was going to happen here, and it did. Try one more. When's this one? No, we don't want like that. Got to pick one. Okay, my last question for today is going to be question 8, or at least one like it. It's another one of those 45-degree guys. So here's A, here's B, here's C. 45 degrees, right angle, 45 degrees. And we are told that A is, yikes, 14 square root of 2. Okay, that's fine. We're going to find out who B is, and then we're going to find out who C is, and that'll be the end of the question. Right, let's get the easy one over with first. If A is 14 square root of 2s, would you agree that B is also 14 square root of 2s? Right. If these two are the same, 45, won't these two be the same as well? So now we can do Pythagoras. C squared is A squared plus B squared. And that's why I went, oh, because I knew this was going to happen. (14 square root of 2 squared plus 14 square root of 2 squared). Would you agree that doesn't look very promising? It looks like it's going to be really awkward. And it could be, except bracket 14 times square root of 2 squared plus bracket 14 times square root of 2. Hopefully I put enough brackets here. And the answer is 784. Now, if you didn't want to do that calculation by just letting the calculator do it, this is what that guy looks like. It's 14 square root of 2s times itself, which means it's 14 times 14 times square root of 2 times square root of 2. Those guys get you 2, and that guy there gets you whatever 14 times 14 is. And that's 196. And 2 times, did I do that right? I think I might have got the wrong answer here, guys. But it's getting late in the day. That's 196 times 2. It's 392. I did. I bet you I forgot on my calculator to do a square root. So I'm going to do the same calculation. Oh no, take it back. I was right. That's only what this guy is. Isn't this guy also 392? And that's where the 784. So I was right. Phew. Okay, so C squared equals A squared plus B squared was 14 square root of 2s squared plus 14 square root of 2s squared, which you could just say 392 plus 392 if you like, but whatever way you do it, you still end up with that. But thank goodness you don't have a lot of these guys to do, okay? Because if you did, you'd be here all day. But this guy simplifies. So here's my analogy. if someone gave you a ridiculous fraction to simplify, you might not find the best number, but can't you at least find some number that works? So I would be saying, okay, I might not be able to find anything, but at least I can divide everybody by 2. And then, you know, play on it. Maybe there's some more, and off you go. So 784. It's got to split. Where's my little list? But this little list can keep on going. I will take any split at all that works. Can you find any way of taking 784 and using one of these numbers times what's left? And anything will do. And I don't care if it's small, medium, or big. Just pick a number that works. And we'll show you how you can slowly but surely get the final answer. So Sarah's hitting buttons, so she might be looking for one as we speak. Anybody got any gut feelings for a number that might work? And we'll check it out.
4.
I would go for 4 only because it's one of the easiest. Let's check it out. 784 divided by 4 gets me 196. Okay, so that splits as 4 and 196. Now, do you see my job has just got a little bit easier? Don't I only need to figure out how to break 196? Has anybody got an idea of what might work with 196?
28.
Well, it might, but it has to be one of these guys. So it has to be one of these or it isn't allowed.
Oh, sorry.
Yeah, that's okay. Hey, if you can't think of a big one, think of a little number that works. It's okay to think of little numbers in this question, because this is a kind of ultimate horrible one you finish with. What can 196 work with?
2.
Well, it has to be one of these numbers, right? 2 works, but it isn't allowed.
4.
4 does work. Yeah, let's just stick to 4s until we get something we can work with. Okay, so it's going to be 4 times something. So I'll go 196. Hopefully it does divide by 4 or that was wasted. And we got 49. So that's 2 times square root of 4 times square root of 49. That's 2 times 2 times. Hey, wait a minute. I think I know this guy. Square root of 49.
7.
The little darlings. It was a perfect number. It wasn't even a square root. Phew. Finito. Stick a fork in it. I don't know about you, but I'm done. Right?